Hello, and welcome to Lecture 2 of Computational Physics course, PHYS-352. As always, I am your instructor, Sasha Chekhovskoy, and today we're going to dive deeper into the C language. In this class, we will start with a brief review of the C language fundamentals. We will talk about C basics and background, the ways to input and output data, both to terminal and file. We're going to discuss how to work with the variables and various operators and control the logic and flow of the program using while, for, and if statements. This review of C language is targeted for this kind of course. And so we will not be able to cover all of the aspects of the C language. So some we will cover only lightly and some we will have to skip due to time constraints. But if you have questions about specific features that you are interested for your work, for your hobbies, or in general, just let me know. I'm always happy to point you to the right resource. With that, let us dive in. C is a language that's high level and compiled. High level means that you have a special syntax for the language and you write the syntax using symbols. So programs are human readable and not going to be directly understood by the computer. So you have to compile the program. So this is the additional step that converts the program from human readable to machine readable format. So this process of compilation produces machine code that computer can understand. And then once that code is created, then it is executed so that it actually does something that you want the computer to do and spits out the result. So let's take a look at an example of how that might work. Let's say that your intent is to print out hello world onto the screen. So you first going to open an editor and create a file that we will call hello.c. And in this file, you will put in the following contents that we will go over especially later. Then you compile this human readable C code into machine code that is definitely not human readable. And after you've gotten that machine code, you can execute it, which will eventually print out hello world onto the screen. So far, so good? Excellent. So what is happening behind the scenes? Well, behind the scenes, a CPU, something like this. This is one of the most powerful, I think actually today the most powerful AMD CPU, which has 64 cores, released a little bit less than a year ago on February 7, 2020. This one goes for $5,200 or so. It's a really powerful CPU, basically an entire computational cluster in one box. So this CPU does what it asks you to do, and you ask it by taking the C code, compiling it in the machine code, and running it. So for instance, an operation like adding two numbers will require several low-level actions from the CPU and the OS. So how does it work? The compiler is what helps to make everything going. First, the compiler scans through the C code and performs the preprocessing. So it substitutes some symbols, includes the code from various files according to instructions. We will be discussing some of these topics later. Then it compiles the code. So it takes the readable code, human readable code, and creates the machine specific code that is very close to the actual instructions that the CPU will receive. And then it assembles it to the machine-coded object files that then will be linked to the libraries that the code uses. So for instance, if you ask the code to print something, it will go to the library that's responsible for printing, pull out the required code, and include it into your file. Or it might do it on the fly if the libraries are dynamically linked. As a result, you'll get something like this that can be run on the machine. So let's take a look at our very first Hello World program. It looks just like that. And on the next slide, we're going to parse this. So the first line is including the information from the standard C input-output library. This allows us to print things on the screen. But before we get to the printing, let's take a look at this statement main. This defines the main function that in this case takes no arguments. It can, in principle, take arguments, and we can talk about that later. And the braces enclose the body of the function. So everything in between the open and close brace is what's going to be executed. This printf is the call to the standard input-output library function that prints on the screen. And you can see, you recognize most of the things over here. Hello world, so this is a string, it's taken in quotes. The \n character is a special character that creates a new line. \n stands for new line. There are a bunch of such special characters. \r is carriage return, for instance, and there are others. We will see more examples of such special characters later. So it's a combination of backslash followed by a character. And if you look it up, special characters C, you will get a whole list of them. And finally, one last point to note here is that in the C language, the statements end with a semicolon, and you can have more than one such statement on a single line. So C language can be quite compact, which is on the one hand nice that it doesn't take up much space. On the other hand, it might be a little bit difficult to read. So you have to put an effort to make sure that the source code is readable, because it's very easy to make it so dense that it's hard to parse. So now it's your turn to try code it up and compile the code. You can do it either after watching the entire lecture video, or you can pause the video right now and try it out. It's up to you. I recommend that you try it out right now, because it is so much nicer to try and get a hands-on experience of how all these things work, not just in theory, but in practice. So once you've typed up that code or pulled the code from the examples associated with lecture 2, take a look at that folder, examples folder /lecture 2 on Quest supercomputer. You can then execute the following line: gcc, which is the compiler, hello.c, this is the file with the source code, -o tells the compiler what name of the executable to create. And then once you've created the executable, you can run it by typing / the executable name. Try it out right now. Well, I presume you've already done that. You can unpause me now, and we can now compare our results. The output should be simply hello world. If you have trouble compiling it for some reason or running it, please post a message to Slack channel. If you don't have access to the Slack channel, please send me an email, and we will work it out to make sure that you are able to do so. So let's try and go over the details a little bit now that you've enjoyed getting your first program compiled and run. So the main function is the entry point to the program that you created. So if you want your C program to run, you have to define the main function. There are exceptions when you don't have to create the main function, and that is if you create the libraries or the object files that will be included as part of another program that does have the main function. We will be talking about this later, so don't stress out if this doesn't make complete sense. There was also function declaration present, although it mightn't have been apparent when you looked at it first. And that's because external functions, such as printf function, the one that we use to print the string hello world, they have to be declared before they can be used in your program. And that is because the compiler needs to know A, what is the syntax of the function, what is it that the arguments it takes, and what is it that it returns. So this is accomplished by including the standard io.h header file. Remember, we started the file with this line, include stdio.h, and that's precisely where the declaration of printf is sitting. You can actually open it up and see for yourself. Finally, you also have to provide the function definition. Finally, you also need to provide the function definition, not only the way to use it, that is what are the arguments and what are the returns. You also need to provide the code for that function, the one that will be run by the machine. And this is all hidden under the reps. You don't really have to worry about that unless something doesn't work and goes south. And in this case, the code for printf is pulled from the standard C library. We will talk more about that later. Now, let's get to how to define and use the variables. And in this case, C puts a little bit of work on us, the people who program. That is because C is a typed language. That is, every variable has a type, and you have to specifically declare every variable alongside its type. For instance, Python doesn't require variable declarations, and it guesses the type of the variable from the way you use it. So in C, you have to specify the type explicitly, and not every operation would make sense. For instance, you cannot add up a string and a number. That just doesn't make any sense. There are a bunch of basic C types. For instance, a signed integer type or an int, a character, which is worth 1 byte in size or 8 bits. So it can go from -127 to +128. Float, it's a 32 in size, so 32 bits in size typically, and double precision float, which is twice as large typically, and the standard size is 64 bits, but sometimes it can be larger depending on the machine. You have to declare a variable before it is used. You typically want to do that at the start of a function. Some C extensions or C++ extension, for instance, allows you to declare variables after any open brace. We can talk about this more later. Another best practice, if you want to avoid using variables that you haven't defined yet, you can haven't initialized yet. You want to set the variable values perhaps at the same place where you first introduced them. This, however, has some downsides because once you have initialized the variable with a specific value, it means that the compiler has to keep track of what its value is, and that uses up the caches, which are limited. So if your program is simple and fits within the caches, then go ahead and do that. But if you have a complicated algorithm that is crucial, that it runs very fast, then you actually don't want to initialize the variables until just before you use them for the first time. That way you will minimize the number of variable values that will be sitting in the cache and will make life easier for the compiler and for yourself because your program will run much faster. So if all of your variables fit within the caches, then it will be much faster because caches are the fastest types of memory that the program has access to. So let's take a look at another example where we can actually use the variables. and we'll call this example hello foobar.c, very descriptive clearly. So this will be an extension of hello.c with the variables. So the beginning is similar enough, but now we can create two variables, foo and bar. Foo will be an integer equal to the current year, 2021, and bar will be the first few digits of pi, 3.14159. You can see that every statement is finished with a semicolon, and now we can actually print these variable values. Printf allows you to do that by using format specifiers, which we will cover in the next few slides. So you can add a %d specifier, which is going to represent an integer, foo, and a %f specifier, which represents the float. So let's dive deeper into this. So an integer, foo, and a floating variable, bar, just as we said. The f in the printf means that it is a formatted print, and that's precisely why you have those format specifiers in order to print various types of variables. So these format specifiers or tokens, they start with the % in the string argument, and %d is an integer, %f is a float. So there is a special notation that tells printf what we want it to do and what sort of format we want to use when printing. We will not go into the details right now. But let's now talk about the operators that allow us to operate on the variables. So there is basic math, there are assignments, there are relational operators, which one is greater, which one is smaller, and the logical operators. There is more operators associated with addresses. We will touch upon them later. So these are pretty clear: plus, minus, division, multiplication. This one is modulus. So 5 modulus 2 will give you 1. So it's a remainder of the integer division. These ones are compound assignments. So let's say I is equal to 0 means that we will assign value of 0 to I. I plus equal to 1, it means that we were going to add 1 to I and place the answer into I itself. So it's going to be an addition plus the assignment in one go, and similar with the subtraction, multiplication, and division. So I divided equal to 2 is going to divide the value of I by 2 and place the output into the result into I. Plus plus and minus minus are doing our equivalent to essentially our equivalent to plus equals 1 and minus equals 1. So plus plus will add 1 to the variable and place the result into the variable, and minus minus will subtract 1 and place the result as well. These are the logical and, or, and not. And this one obviously is not equal. So exclamation equal sign is not equal. Notice that two equality signs is a logical operator that compares two numbers, and it is different than the assignment operator with one single sign. So if you say I equals to 1, you are assigning 1 to I. If you say I equals to 1, you're comparing I to 1, and there is no assignment happening. In this later case, I value is not changed. So let's try and see how we can use these operators in real life. Now we're going to update hello foobar with these operations. So now let's see that we are adding two header files, standard input output and standard math. We are now using pre-compiler directives, which are also referred to as defines. So what that means is that when the compiler takes a first pass on the file, all the instances of my foo will be replaced with 2020, and all the instances of my pi will be replaced with 3.14159. So we will start our main program as before. We will assign my foo to foo and my pi to bar. This is nice because all of these parameters are sitting right at the beginning of the program, so you can clearly see what are the knobs that you can turn as a user. And let's take a look at what's going on with the program. First, we're going to say it's hello world clearly, and then we're going to print out basically the same as what we did before. We're going to print out foo, which will be 2020, and then we're going to print out bar, which will be the value of pi. And you can see that in this format specifier %.4f, .4 means we're going to print out 4 significant digits. And that's why when we print it out, it appears as 3.1416. So the last 9 and the 5 get combined, get rounded up to 6. So the first line of output is pretty clear. That's precisely what we wanted it to print. The second one, before we print, we increment the value of foo by 1, foo plus plus, adds 1 to foo and places the output into foo variable. And the second one multiplies the value of bar by a factor of 2 and places the result into bar as well. So foo will be incremented by 1 and bar will be doubled. So let's take a look at the output. Indeed, foo is now 2021 and bar is 2 pi, still rounded up to 4 significant digits. Now we're going to get into the weeds of how integer division multiplication work. We're going to divide foo by a factor of 3 and set bar to 3 times foo. So if we integer divide 2021 by 3, you actually will get a fractional answer. It's not cleanly divisible by 3. And what integer divide does, it throws away all of the fractional parts, retaining only the integer part. So for positive integers, it rounds it down to the nearest whole number. So that will be 673. And then when we multiply 673 by a factor of 3, we actually are going to get 2019. So you see that if you perform these operations of division multiplication using integers, you can lose significant digits because the operations involve only integers. So let's take a look at it again. So we use define preprocessing here in order to keep the variables defined at the beginning where they're easily accessible. As we discussed, the compiler replaces these symbols, my foo and my pi, with the values. And in here, we are using the integer division, foo divided equal sign 3. And that's why we're not getting 2021 here, we're getting 2019, which is divisible by 3, unlike 2021. Now we can get to the next exciting topic of input and output. How does our program communicate with the external world? Because before that, the only way it could do so is through those defines, where we could come into the program, change the variable values, and recompile and run it. Whereas now we're going to try to input the data directly from the external world. So let's try and explore character input-output. This we can do through a call to get char. It returns a character that you tapped on the keyboard. And in order to output something to the screen, you can use putchar, which puts the character that you supplied as an argument to putchar onto the screen. So this is much simpler than printf. It also has much more limited functionality because printf spits out an entire string on the screen, whereas here we would have to spit out characters one by one. It can handle a string, it can only handle a single character. So let's take a look at an example, including our header file first, starting the main function. We are using printf to invite the user to input a character. Then we're going to poll the keyboard for that character. So we create a new variable of type char, C, and we assign it to the output of function getChar. And once this function returns, it means that it has detected a character press, and now we can use putchar to print it out onto the screen. So that's exactly what we've done. We declared and initialized the character variable with a value that we fetched from the keyboard. And then using putChar, we're going to print out this character onto the screen, onto the terminal. And we'll also print out another one, the new line character that we already discussed. As you see, we have to separate them out because putChar can only handle one character at a time. So 2 characters, 2 calls. So now it's your turn. Try code and compile that. And you can press pause on this video to try and see what's next. So let's try and play around with this software that we wrote. This is how it will look like if we type in ABC. And you can see that as a result, the output would be simply A. It only prints out the very first character you enter. It ignores the rest. And so that's not super satisfying. In order to be able to input an entire string, we're going to use some conditional statements, maybe loops, or the flow control. So this flow control is achieved using while and if, else, if statements. So the example of a loop that's perhaps the simplest is such. While with the expression here, followed by some statements which are enclosed in the curly braces. If we want to control the logical flow or function, we can have if, else, if, and else sequence of statements. So if this expression is true, the statements will be carried out, and then the rest of them will be ignored. If the first one is not true, we're going to go to the else if, the second statement, and we'll check the truthfulness whether the expression 2 is true. And we'll discuss what truth means in the language of C. It will then carry out the other statements if expression 2 is deemed to be true. And if neither of these is true, then it will go into the else statement and carry this out. So what is the truth of a statement or false of the statement according to C? The statements evaluate to either 1, which is true, or 0, that is false. So if you say 1 less than 2, that is a true statement, and C will evaluate it to 1. If you say 1 less than 1, it's a false statement, and C will evaluate to 0. If you check the truthfulness of an expression, like you can do here, if 5, for instance, you can say, you can do that. 0 will be interpreted as false, and everything else will be interpreted as true. So if you put if 5, that expression will be deemed true and will carry out the statements that follow. So let's take a look at how this works in practice. But before we do that, let's go into details about the while loop. So if you say while expression followed by the statements will keep executing while the expression is true. It's very easy to get the software be stuck in an infinite loop if you don't update the expression itself, so it always remains true. So if your software is stuck, well, you then go and kill it using the kill command, and you will go back and see what was going on wrong. You can also get out of the while loop by using the following break and continue commands. Break means that the loop will be stopped from execution, and continue means that the rest of the loop will be skipped and you will go to the next loop iteration. And of course, you can have any combination of if and while constructs, as we will see on the next example. So here's the nested example of while, if, and continue statements. So let's dive in deeper to try and absorb the details. So here, first we switch off the buffering of the output so that if the program finishes prematurely, everything that it sent to print to the terminal will actually make it there. Otherwise, if program gets killed prematurely, before the buffers were flushed, then you might never be able to see the output. So that is a good thing. If you're debugging software, you can set the buffer size to be null, and then there will be no buffering for the output. That will slow down the printing or the output to the terminal, but good for debugging. So now that we have done all these preliminaries, let us try and make a loop that will keep looping while the value of I will be greater than 0. And it starts at 5, so we will definitely enter this loop the first time. Let's skip this line for now. It only will be activated once I is equal to 3. And the first time we enter here, we're going to have I equal to 5. So it doesn't activate it first. Then we're going to assign the value of variable j, which is also an integer, right? They were both declared as integers, to be equal to I. And that is because now we can loop over j. While j is greater than 0, we're going to print the value of j, take a pause for 1 second, and then decrement the value of j by 1. So in here, we're going to start with 5 because I was initially 5 and j was initially I, and we're going to print out 5, 4, 3, 2, 1, and then we're going to do the liftoff. So that's the first iteration on I. After liftoff, we're going to decrement the value of I, going to come back here, and the same exact thing will happen for 4, except now we start not with the value of 5, but with the value of 4. That's why 4 is printed. Once we get to 3, this iteration is going to be skipped, because if I is equal to 3, we're going to decrement the value of I, but we're going to continue to the next iteration of the while loop. So that's why the line starting with 3 is missing in the output, because of this continue statement. Continue statement stops the execution of that iteration of the loop where it's encountered, and sends us to the next iteration. Make sense? That's why we get here for I equals to 2, where we're going to do exactly the same set of steps, except now we start with 2. And then we're going to get to 1, after which I will be decremented by 1, it will be equal to 0, and the expression here in the while loop will no longer be true, and the program will end. Does that make sense? Great. So now let's try to deal with the input such that we can input not just one character, but many characters. And that we will achieve by using a combination of while loops, and we have it right here. So the program starts just as before. We include standard input-output library. We start our main function, declare a character variable c, print out a prompt, and we're going to loop while c is not equal to an end of file. You can see that there is already a problem with this code, because we haven't assigned the value of c to anything. Its value can be filled with garbage, and we're checking the value of c right away. So this is an example when the compiler will complain if you try and compile it by telling you that you're using an initialized variable. So in order to fix that, in your version of the code, you can set c to anything other than the end of file, which typically is -1. So if you set c equal to 0, then this code will be good, right? So this is an example of how not to do things. So once we have fixed that bug, now the code will work robustly, and as long as c is not equal to the end of file, we're going to request an input of a character. We're going to print out the value of that character followed by a new line. And we're going to keep looping until we input the end of file from the command line. And once we're done, we will print out Finny, and we're going to be happy. So this is the typical output. If we enter A, B, C, press enter, and then press Control D to send the end of file. And that's exactly what you're going to get. You're going to print out A, B, and C. then when we enter, it will actually print out the actual new line character. That's why there is an empty line over here. Once you press Ctrl-D, it will print out whatever character stands for the end of file. And after that, we're going to declare victory and say that we have accomplished the mission. So this is great, but the output doesn't look that awesome, right? Every character is printed on its new line, and we're also printing out the new line character and the end of file characters. That's not awesome, right? So if we want the client to be happy, we want our software to be eye candy. So let's try and improve on these. So we will call this get lots of cars, and we're going to include conditions here. So the beginning is very similar. There is still the same exact bug where we need to define the value of C. We need to initialize the C to any value other than the end of file. We are going to input a character as before, but now we're going to check. Is the fetched character a new line or end of file? If it is not, then we're going to print out the character, print out a new line, and then we're going to continue looping. However, if it is an end of file, then we're going to call it quits. So this is how the output now will look like. If we enter A, B, C, enter, Control-D, and enter, we're going to not see the enter or Control-D printed out. But other than that, we still are getting one character printed out per line. Wouldn't it be nice if we could somehow put the characters together in a line and print them out as a line if we actually want to see what we input? Let's try and do that. But for that, we will need some conditional logic here for the for loop. And we're going to have to find a way to put these characters together. And this is what we're going to use a character array for. So we also are going to take a look at another loop construct, a for loop. The for loop looks a little bit more complicated than the while loop. Whereas while loop only had one expression, in for loop there are three expressions. Expression 1, 2, and 3, followed by statements. Expression 1 is executed before the loop. Expression 2 is checked upon entry into the loop. And expression 3 is performed at the very end of the iteration. So an equivalent code to this for loop would be expression 1, while expression 2 statements, expression 3, and the end of the loop. So this and that are equivalent, but this is much more compact and easier to read. So let's try and rework our countdown liftoff example using a bunch of nested for loops. So here, as before, we include the standard header, announce our main function, and we are going to create two variables, I and j. Note that you do not have to have just one variable per initialization. You can have multiple variables. So here we do int I comma j. Their values are not initialized, but they're declared that both I and j are integers. Now, in the for loop, we start by initializing, finally, our variable I to 5. We're going to keep looping while I is greater than 0. And at the end of every iteration, we're going to decrement the value of I by 1. So as before, we're going to skip an iteration if I is equal to 3. And then in order to do the liftoff, we are going to loop over j, which is initialized to I. We're going to keep looking until j is greater than 0. And we're going to keep decrementing the value of j every time. Once we are done with the looping over j, we're going to print out liftoff, and we're going to keep on decrementing the values of I. So we're going to get exactly the same output as we saw before when we weren't using the for loops, but we used the while loops. In order to be able to print out a string, as we discussed, we would need to work with character arrays. And we can construct arrays of any basic C types. But you need to tell the compiler how many elements you want the array to hold. And you specify this length of the array in the declaration. For instance, if you want to create an array of integers of 10 elements, then you type int a of 10. In order to access the elements, like shown here, you can write a of 0 using square brackets. That will refer to the very first element of the array, but because all the indices in C starts with 0, it means that the first element of the array is actually 0th element. So it will be a of 0, followed by a of 1, and ending with a of 9. Again, because the indexing starts with 0, it means that the last element will be 9th, not 10th. If you were to refer to a of 10, that will be bad, because you would be accessing the memory that doesn't belong to the array, and the value of a of 10 is not going to be defined. It's possible the program will crash or its behavior will be unpredictable. So that brings us to the next point, that there is no bounds checking in the C programs. We will see later how we can compile the program in a special way such that there is a way to actually do that, but that's typically used while debugging the software. If you already know that there is something wrong, you want to see, is this an out-of-bound exception that you are running into? Or if you just want to do pre-production check of your program to make sure everything is working fine. This is a really bad problem to have, because this is typically how hacks have been performed. If you manage to get an overflow error, this memory access to parts of the memory that don't belong to you, that way hackers can craft an attack that will allow them to take over the computer, basically execute the code of their desired behavior. So buffer overflow are really popular attacks. Have to be very careful and make sure that if you define an array of a certain length, that your code is careful not to access something that is beyond the end of the array or before the beginning. If you supply a negative index, you can actually access something that is before the array, which is also not good. So you can also implement two-dimensional arrays. So for instance, you can have two values in brackets, one after the other, and this will be an array that has 2 dimensions. The first dimension has 2 elements, and the second dimension has 10 elements. And you can initialize arrays statically, like this, for instance, in which case you don't have to specify the number of elements in the array. Because you specified the elements in the initialization, the compiler will figure out what is the size of the array to hold these elements. In this case, it will be an array of size 4. If you were to set char a equal to abc in quotes, this and that would be equivalent. Note that abc in quotes is a string, and strings are represented in C via a character array terminated by the 0 character, the end of string character, which is a special character, just like \n. This one is \0. The code of this character is actually 0. And so this is how C knows that ABC is a string, and there is nothing more beyond that. That's where the end is, because 0 character is a special character that is specifically used just for that purpose. So now let's try and use the for loop and an array in order to make our output look amazing. So this is our new glorified get lots of chars 3.c, where we're using static array declarations initially with an array size of 3. Watch out for buffer overflow. That will be our home problem set. Notice that again, C is not initialized, so that is an issue. So something that you will need to fix as well. We're going to initialize the value of I to 0, and we will not initialize the value of j initially because it will be initialized later. And we're going to loop until C is the end of file. We're going to request the user to input a character. We're going to break the whole logic if the user inputs the end of line character, the end of file character. And we're going to keep looping until the character is an end of line. If it is, we're going to, if it is not an end of line character, then we're going to assign it to the next position in the array and increment the position. And if it is an end of line character, we're going to print out the input, and we're going to do so by looping over the entire array and printing it out. Finally, we will wrap it up by printing a new line character, and we're going to declare victory by printing out Fini. There are a bunch of problems here, one of which I already mentioned, but there are also others. So that will be part of the home problem in order to make sure that this code is clean and secure and safe. Copy this code and compile it, and test it by entering ABC enter Control D enter, which will now actually be able to print out the entire line as we wanted. So in the home problem, we will address the issues that the code has that we haven't yet covered. There is another way of inputting characters. So far we did so manually, and we had to input them one by one. However, we can rely on the libraries, input and output libraries, to do a whole string input for us using the scanf function. For instance, we can do so this way. We can make a call to scanf, specify the types of variables we would like to read in and the format in the string, and then provide scanf with addresses at which to place the scan variable values. So for instance, here we would like to scan a date like 14th of January 2021. And to do that, we're going to tell scanf that the first argument is an integer, %d, followed by a dash, which it will skip. Then it will look for the next integer, in which case it would be 14. And then there will be a dash. Finally, there will be the last integer, the year 2021. And because scanf needs to know not just the value of the month, day, and year, it needs to know where these variables are stored in memory, that is the addresses. In order to update the values of these variables, we provide it with the address of the day, which we do with the ampersand sign, just like the slide explains here, for all of these three variables. So day itself could be a number, 1, and ampersand day will be the number of bytes from the beginning of memory till the place where day is stored in memory. So scanf figures out where the day variable is in memory by its address. The address is what it is, the position memory, goes there and replaces the bytes that encode the value of day. That's why we need to provide the address by using the ampersand sign. I hope that's clear. We will talk more about the addresses later next week. So here is how we can incorporate scanf in our new algorithm for reading in the strings. So the beginning is basically the same, except now we have an array size which is bigger, 256 characters. As before, we start the main function, open the curly brace to tell the compiler that now is the body of the function. Beyond the curly brace, we're going to define the array of that size. We're going to scanf a string into our array of that size, and we're going to print out whatever we scanned. Next time, we're going to try and actually interpret the input. So we're going to now request the user to input today's date. And now we will define the variables for month, day, and year. And we use the newly acquired knowledge of how to use the scanf call in order to convert the string into month, day, and year. And finally, we're going to print out the answer. Notice that in both cases, whenever we use scanf, we provide the addresses in memory where scanf is going to place the values of Fred in parameters. So for instance, here, CArray is actually the address of the first element of our array of characters, and so that's why we put in CArray in there. In the case of the integer variables, we're going to provide the address of the month, the day, and the year using the ampersand signs. So this is the output, and you should try and compile this code, run it, and play around with it yourself. So for instance, you can, when you run it, it will ask you for a string. If we input hello, it will print out hello. And when it asks for today's date, we're going to input the date like this, and it will print it out like that. You see, because we have converted the date into the constituent numbers for the month, day, and year, we now can print these numbers using different separators. So we went from the dashes to the slashes. And the bottom line here is we can read more than a single character, an entire string. But sometimes you actually want to read the data from a file and output the result to a file, because it's not practical to type up the data manually in the command line or in the terminal. So let's try and see how we can work with files. And file input output is done by making a call to fopen that opens a file, and it returns a structure, rather a pointer to a structure that describes the file itself. So we will talk about pointers more next week. So far, what we care about is that the file name here is a character string. Access mode here is also a character string. And you can basically use it to tell fopen what is the mode of access to the new file that you would like. You can either open it as a read-only file if you provide R in quotes. You can read it with the ability to write to the file as well. That would be R+. And if you open it with W+, you will create a new file and will be able to update the file. So how do we read from the file? You can read from the file using the file analog of scanf, fscanf. Not surprisingly, there's an extra F at the beginning. And it requires you to provide an extra argument, the pointer to the file, as the first variable that you supply to fscanf. You can also print to the file by using the printf analog, which is fprintf. Again, the very first argument that you're going to provide is going to be the pointer to the file, followed by the format string, followed by the arguments. So here's an example of how you can convert whatever you input from Fahrenheit to Celsius. So far, we're going to be reading the data from the terminal. So as usual, we have our header files, in this case, standard input output, our main function, and we're going to introduce the variables that hold temperature in Fahrenheit and in Celsius. We're going to print out the user instructions to enter the temperature in Fahrenheit. We're going to scan F. We're going to scan the input for the temperature in Fahrenheit, convert into Celsius using the regular formula, subtract 32 degrees from Fahrenheit, and divide the result by 9 multiplied by 5. And we're going to print out the temperature in Celsius with one significant digit, so not too many digits to overwhelm the user. So here's an example of how this program works. You enter the temperature in Fahrenheit. In this case, we're going to enter something that we know the answer to. 212 is the boiling temperature of water, and we're going to end up getting 100 degrees centigrade as the output, which is also the boiling temperature of water. You can also try inputting -40 and see what you're going to get. So let's now try and input the data not from the terminal. We can use this file which is a comma-separated spreadsheet, as the file name, and we will open it in the read-only mode, in the R mode. And we're going to output the result to this file that we will open it in the W+ mode. So you can get this data from here, and there are four columns in this file. The date, the high and average and low temperatures in Chicago for every day of the year 2012. So you can see the format. The first line is the header line, and then you see the date followed by 3 temperatures. So here is the function, here's a program that will allow us to accomplish the task. Read the file, convert all the temperatures to centigrade from Fahrenheit, and write it out. So first, we are going to, as before, include the standard libraries. We're going to start our main function, declare the variables. We're going to open 2 files, the input file and the output file. The first one will be open in the read-only mode, and the second one will be open in the mode in which we can write to a file. So we will need to first, remember, skip the header because it doesn't contain useful information, which is what we will accomplish by scanfing the first line, and the asterisk here, or star, tells us that while we wanted to read an entire line, we don't want to save it anywhere. That's what the star does in the format specifier for fscanf. Now we're going to keep reading line by line the contents of the file, and we're going to keep doing that until fscanf returns the end of file, meaning there's nothing more to read. We've exhausted the file. fscanf reads from the input file. This is the format specifier, the 3 integers forming a date and 3 floats giving us the high, average, and low temperatures. We're going to provide the addresses for each of these 6 variables. 3 variables describing the date, the year, month, and day, and 3 variables describing the 3 temperatures, high, average, and low for every day. Once we have successfully read one line, we are going to convert each of the 3 temperatures from Fahrenheit to Celsius, and we're going to print out the result of the conversion of this line to the output file. Once we're done with all of this, we're going to close the output and input files. It's really important. We don't want to leave the file dangling, because then the writes might not be completely safe to the file. Files might be corrupted. This is really important. If you open a file, you always want to close it before the program ends. So here you can notice that we use these weird kind of brackets, braces, parentheses, slash star. This sort of brackets, parentheses, they enclose comments in the C language. One other interesting note here is that we place the entire function inside of the while loop expression. You don't have to call the function, save its value, and then call the while loop. You can do it all in one go, which is an advantage of C language. It allows you for additional extra flexibility. You also know that you can span several lines with the call to a function. Because the end of a statement is denoted by semicolon, the C compiler knows that all of the 3 lines belong to one single function call, fprintf. However, be careful, because you actually are responsible for making your code readable, so this extra flexibility in crafting the C code might lead to the code being not super readable. Python is much more constraining and typically forces you to indent the code and make it readable by construction. So that's why sometimes it's easier to read Python code than the C code. However, this is not really a downside of C. It just gives you as much flexibility as possible. So if you follow nice conventions and indent the code and make it readable, it will be readable and nice for consumption, not just by you, but by other people who come after you and will be using that code. So this is what the expected output looks like. We have the dates in slightly new format, followed by temperatures in centigrade. And you can tell it's centigrade because you have a bunch of negative values. Chicago is cold in the winter, but it doesn't get quite negative so that you will get negative temperatures in Fahrenheit. So in centigrade though, sure. I mean, -1 is just below freezing, not too bad, which is what we currently have right now. So this does it for us tonight. Thank you so much for your attention. There is a lot more exciting material to come. We're going to fill in some of the details. We're going to talk more about functions, arrays, and pointers, and we're going to go into the structures, of which we saw some examples already, like the file structure. And we saw some examples of pointers as well, but we're actually going to talk more about how to use them, how to define them, and how to make the most out of all of these to make the code writing easier, more efficient, and easy to understand for other people who will come and use your code. Thanks again for your attention. Hope this was fun, and I'm going to see you in lecture 3, and maybe even before then, I'm going to see you during the office hours. Have a wonderful rest of the weekend, and I'm going to see you soon.